Hey there, I'm just doing a video on my Tesla Hairpin Circuit variation, and now I've varied my variation circle a lot and have successfully got like much better tuning. So now it's not just semi-solid state, it is solid state. So cross that out. Lower voltage solid state Tesla Hairpin Circuit variation. Things I've changed. Instead of the ferrite ring that I was using, which is right here, I'm not using it because it's not needed, and these things like to be resonant at a lower frequency, and it's just not proper for the circuit, I don't think. So I've replaced that with this guy, and a lot of you probably recognize this. This is the coil out of a microwave oven, an old microwave oven fan. And it's an AC fan, and if you're salvaging parts, you can get these coils really easily, break it down, and on top of it, I just want to add this. These are awesome variable inductors, because this part pops out with it, and yeah, that's soft iron in layers, and you can slide that in and out of this relatively easy. Well, I'm not making it look easy right now, but you can relatively easy. I have to pull that out. Give me 1 second. There we go. And yeah, it's a variable inductor in the millihenry range. But anyways, I wrapped, what is it, 15 meters, 50 feet of 22 AWG on the outside for the primary. So, and it has on the inside of it 22 ohms of what looked like about 28 AWG, I'd say, roughly 22 ohms. So yeah, I've replaced this. This is now air core, 22 AWG primary, 0.8 ohms, about 15 meters, 49 feet. The secondary is about 22 ohms. I put the caps that were in parallel in there in series now. So now, instead of having 20 nanofarad, it's in series, so they're 5 nanofarad each. I got rid of the spark gap because I have a suspicion that when Tesla was doing this stuff originally, he put the spark gap in there to act as a high frequency oscillator between the caps, because it wasn't easy with a rotary commutator to get like really high radio frequencies going on back then, and they didn't have signal generators, so you'd have the commutator, some sort of iron core transformer, then the spark gap would step up the frequency. Now that's just my sneaking suspicion. The frequency I'm running this at is 29.1 kilohertz, 38% duty cycle. And yeah, I have the probe up here. In the probe I have 5 megohms of resistance, so I can get the shot on the scope. Otherwise it just goes out of the scope screen. Alright, so now I have the signal generator on. Turn off the lights. Here we go. So, turn it on. Here we are. You can see nice sine wave. When it's tuned like this, it's just like a beautiful, perfect sine wave. There it is 11 volts, quarter of an amp. 19 volts, 0.4 of an amp. 24. Still a beautiful sine wave. That's we'll go up to, let's put her up to 45 volts. There's 46 volts at an amp. Still a really nice sine wave here. Yeah, it's just really good. It's it's bright. It's quite bright. There's a lot of heat coming off of it, and it's just working like a standard transformer circuit. It's been fun though. I was with the other one, I was changing capacitance values, trying all sorts of stuff out. Couldn't really get her to go good. I'll show you right here. If I put the there, oh darn it. Okay, so we're back again. Yeah, I was going to attempt to show you how the gas discharge tube or spark gap incorporated into the circuit functioning like this actually kills the efficiency and what actually happened is it killed the MOSFET at 45 volts at an amp. This little IRF Z44N just couldn't take it. Anyways, so yeah, the tuning's down pretty good, I think, and you know, it's I don't know how efficient it's operating, but that's the next step. So I think what I'll do is I'll grab my 100 watt dummy load resistor. I'll run it at about 20 volts, I guess, right about here, about 20 volts, and that'd be about 8.8 watts, and we'll set up a full bridge rectifier into a little cap across the dummy load, and we'll see what we get. So that's the next step. I'll go set that up right now. Okay guys, so I did a setup where on the where the light bulb went, I put a full bridge rectifier across a small cap, and then measured across a 211 ohm 100 watt resistor. Then I did it's the calcs, 4.73 squared divided by 211, and I had an output value, real power of 0.106 watt, and that was when I had 2.6 watts input, which gives us 0.04 percent, or 4% efficiency, or a COP of 4. LOL, because that's horrible. I knew that it was inefficient, but I didn't think it would be that inefficient. But you know, numbers don't lie. And here I just want to show you comparison. This is the bulb running on about, I guess, about 20 watts, 18-20 watts DC, and like I think it's as bright or brighter than it was when I had 40 watts going through the system. So anyways, you know, this is just a venture into the Tesla Hairpin Circuit. Not the most efficient circuit, or at least the way I had it set up wasn't the most efficient circuit. But anyways, it was, I had a lot of fun testing it out. You know, I learned some stuff, and it's cool. Now on to the next one, or back on to the other stuff I'm working on. Oh, and when I built this coil here, it was initially to try and make a Joule Thief with high resistance for my other Vortex coil comparison vid, but couldn't get this one to oscillate either, so that venture continues. Anyways, thanks for watching, guys. You guys all rock, and till next time, peace.